In our modern networks, cryptography has become one of the baseline ways that we protect data in transit and data at rest. Here we'll look at the various components we see used for this, including public key infrastructure. We'll also discuss options for email and disk encryption, as well as common cryptographic attacks and countermeasures. Cryptography is a concept that means we are scrambling data in some way in order to conceal the data from unintended parties. This is so common today that we often take it for granted. Even basic internet browsing through HTTPS uses encryption to provide this feature. In this last course section, I want to make sure you understand encryption from a high level, including important concepts such as algorithms, hashing, and keys. First, let's discuss why cryptography is important. One of the most foundational concepts regarding security is known as the CIA triad. This stands for the three very important pillars of security, which are confidentiality, integrity, and availability. Every organization has what's known as assets that need to be protected, and an asset is simply anything that is valuable to an organization. This can include equipment, trade secrets, database information, accounting information, or any number of other things. So let's zero in here on confidentiality, because one of the main ways that we ensure confidentiality is through cryptography. Confidentiality means that only the individuals authorized to view the data are able to do so. This implies that unauthorized individuals should have no access to our assets, and this applies to both data in rest and data in motion. Data in rest would be information stored in a database, for example, while data in motion would be information transiting the network in some way, such as maybe over a VPN or using TLS, transport layer security. Encryption can and often is used with data at rest, such as encrypting the local hard drive of an end-user device. But encryption should also definitely be a part of any data that's in motion. In either state, whether at rest or in motion, we can use special encryption algorithms to essentially scramble the data so that it cannot be interpreted by anyone who might want to get their hands on it. This is the principal reason that we do encrypt our data when we send it over a network. When it comes to protecting the CIA triad, the two most fundamental cryptography methods are encryption that we've mentioned and hashing. Hashing is the process of generating an output value from a known input value by the use of a mathematical function. The property that makes hashing work is the fact that as long as the input value does not change, the output value will always be the same. Complicated algorithms can quickly compute an output value, although the output value cannot be easily reversed. That is to say, it's difficult to determine the original input value from a known output. These properties make hash algorithms a common and reliable way to ensure data integrity, another piece of our CIA triad. As a very simple example, consider the following input and hash algorithm. We see the input value 4986 and a very simple hash algorithm. Just as an example, we're multiplying the input value by 6563. The input would be inserted into the hash algorithm in order to compute the hash value, and the resulting hash value is just over 32 million as seen here on screen. It would be difficult to determine that the hash value of 32,723,118 came from multiplying together the two numbers 4986 and 6563. And that's because there are many potential multipliers which could have given us this exact same output. Now, with enough time, it is possible to compute and create a list of every potential pair of numbers that would be factors of this output. And that's the exact reason that our modern algorithms are preferably complex, and the complexity is measured by their hash output value length. Generally speaking, the larger our hash value output is, the more secure a hash function is considered to be. Let's compare some of the most common cryptographic hash functions that we see in use today. First, we have MD5, Message Digest 5. This is considered to be a legacy algorithm, and it's not preferable for advanced modern encryption applications, although this is still commonly used for standard file verifications. MD5 produces a 128-bit hash value output. By the way, we also commonly refer to these hash value outputs as message digests, just like the name of this particular function. Next, we have Secure Hash Algorithm 1 or SHA-1. Like MD5, this algorithm is also considered to be legacy and should be avoided when possible, although the larger hash value output does make this more secure against attacks than MD5. SHA-1 creates a 160-bit or 20-byte hash value message digest output. And we have Secure Hash Algorithm 2. This algorithm was designed by the United States National Security Agency, the NSA, and it includes significant changes from its predecessor SHA-1. The SHA-2 family includes functions that can output various hash digest lengths of 224, 256, 384, or 512 bits. It's recommended to use SHA-256 or higher whenever possible. That's going to be the strongest version of these algorithms. Hash algorithms are also commonly used for secure file transfer with protocols such as SFTP and HTTPS, for example. In secure file transfer protocols, this is achieved through a mechanism known as Keyed Hashed Message Authentication Code, or HMAC. This authentication method adds a shared secret key to the input value before the input value is ran through the cryptographic hash function. Using our previous example, this would look like the following. We have the same input value of 4986, but this time we additionally have a secret key value, 17692. You can see our hash algorithm is adding the input value to the secret key before multiplying that by 6563. If we insert our values here, you'll see that our hash value output is just short of 149 million. So notice the larger output value than we previously generated. This inherently means that this is a more secure method. The secret key that we've added is known only by the sender and the receiver of the data, and the hash value output cannot be computed without the secret key. So in addition to data integrity, this also provides proof of message authenticity and the assurance that the two parties exchanging data are in fact authorized sources. If we're talking about the popular usage of this, one place that I use this quite often is in the Cisco world. Cisco employs hashing in several manners. We have the IKE and IPsec protocols, which rely on hashing algorithms to verify packet integrity and authenticity. Cisco iOS routers use HMAC to add authentication information to routing protocol updates. And also Cisco software images have MD5 and SHA-512 checksums available in order to verify the integrity of downloaded software images. This isn't unique to the Cisco world. If we look at things like Parrot OS and Kali Linux, they also provide checksums to verify the integrity of your downloaded software images. If we go out to the Cisco website as an example, you can see that they provide those checksums as a way to verify the integrity of any downloaded software images. So for example, you could download an image onto your computer, you could run the MD5 cryptographic hash against the downloaded image, and compare the output that you get to the one posted here on the Cisco website. This helps to ensure that the image you downloaded has not been tampered with or altered in any way. In regard to encryption, encryption can be either symmetric or asymmetric. Symmetric encryption algorithms are the simplest form of encryption and would involve using only one secret key that would be used to both encrypt and decrypt the data. This is otherwise referred to as secret key encryption. This type of encryption is more lightweight because the key lengths are typically smaller, therefore allowing for the faster computation of those hash values. The main disadvantage of symmetric encryption revolves around secret key security. Because all parties that are exchanging data must have access to the secret key, there's a higher probability for the key to be unintentionally exposed or maliciously intercepted. Common types of symmetric encryption include DES, which creates a 56-bit hash value output length. This is another algorithm that's considered to be legacy and that should not be used. We also have triple DES or 3DES. This creates 112 and 168-bit hash value output lengths. This technique applies the normal DES encryption 3 times in a row with different keys, so that does increase the attack resistance. And we have the most modern and preferred version of this, which is AES. This can create hash value output lengths up to 256 bits. This is the chosen successor to DES and triple DES due to the larger, more secure key length and also the faster computation of hash values. Asymmetric encryption algorithms use a pair of keys to encrypt and decrypt the data, otherwise known as public key cryptography. These algorithms are more complex and secure than symmetric encryption algorithms, but they are more resource intensive to process. The created key pair will consist of one public and one private key. The public key is made available to any party with whom encrypted data exchange is desired, while only the key pair creator will have access to the matching private key. A message that has been encrypted with a public key can only be decrypted using the matching private key. Also, a message encrypted with the private key can only be decrypted using the matching public key. So you can see how these keys work together. With asymmetric encryption, we're not concerned with public key security because that key doesn't match the private key. The public key itself can be freely shared over the public internet. Common types of asymmetric encryption include Diffie-Hellman. This creates various hash value output lengths up to 4096 bits. We also have RSA and DSA creating 512-bit to 1024-bit hash value output lengths. We also have ECC, which creates a 160-bit hash value output length. Additionally, we find asymmetric encryption algorithms in many well-known protocols, including the Internet Key Exchange, or IKE, Secure Sockets Layer, or SSL, Secure Shell, or SSH, and something called PGP, Pretty Good Privacy. Let's look at some cryptography tools that we have available to us, and we've mentioned previously the fact that we can run MD5 or SHA checksums against downloaded files. That's one way that we can ensure that we are downloading the files that have been untampered with or unchanged in any way. As an example of this, if we go out to parrotsec.org, this is where we can actually download the Parrot OS project that we've been using throughout this course. If we look under our download tab, you'll see all the various options for downloading Parrot OS. I, of course, am using the security edition that we have here. One additional place that we can look at, notice there's a section for signed hashes. And if we click on that, this actually shows us the hash values for all of the various images that are available for download. So one common way we might use a cryptography tool such as hashing, again, is to verify file download integrity. So let's actually look at this inside of Parrot OS. Here in my terminal, I'm going to change into the directory home/user/downloads. And if I perform an ls command, you'll see that I actually have an ISO file here for Parrot Security. Just as an example, you'll see Parrot Security 4.11.3, and that is an ISO file. Now, if we want to see the actual checksum value for this, let's say we want to see the MD5 hash. You'll notice that MD5 is one of the values available to us for checking the file integrity of our downloaded file. So back in Parrot OS, in order to do that, we can say MD5 sum followed by the file name. And the file name that we can see is parrot-security-4.11.3_AMD64.ISO. I'll hit enter, and this is going to run the MD5 hash against this file. And in just a moment, it's going to spit out an MD5 checksum. We see that listed here. So let's actually highlight this. Let's copy it. And I already have just a text editor open. And I'm going to paste that inside my text editor. Now I'm going to go down a line. And if we go back in to the Parrot OS website, the particular image that I downloaded was this security version 4.11.3. Again, you see they have an MD5 checksum available here. So I'm going to copy that, and I'm going to paste that in my text editor as well. And of course, you can see that these are identical. So this means that the downloaded file that I have gotten from Parrot OS has not been tampered with in any way. It matches the exact same checksum that is listed on the Parrot OS website. So I can have the assurance that there is file integrity here. In other words, the file hasn't been changed, altered, or tampered with in any way between the time that Parrot OS uploaded this and I downloaded this. Now we can do the exact same thing for any of the different algorithms that we see here. So we see there's a list of these. If we go down and try the SHA-1, we'll go back into our terminal and I'm going to arrow up, and this time instead of MD5 sum, I'm going to say SHA-1 sum. I'll hit enter. While that's running, I'm going to go back into my web browser and I'm going to copy the SHA-1 checksum for my appropriate image. So let's copy this. Let's go back into my text editor. Let me paste that in, and now we see in the terminal that we do have a checksum listed here. Let's copy this as well, paste it into my text editor, and of course we see that these match exactly as well. So that's one option for using a cryptography tool that's built into Linux in order to check the file integrity. And of course we can do a similar function on all of our different operating systems that we happen to be running. Now let's say we want to send a file to someone and we want to generate our own MD5 sum against that file. We could actually perform this exact same procedure against any file that we have. If we were in our terminal and we had a file that we had saved locally, we could generate our own hash values. We could provide them to another party, a recipient of a file maybe, and then we could allow them to run that same hash on their side, and then they would have the assurance that there is file integrity in place. As an alternative option for this, I want to talk about another utility. Let me go back into my main root folder here. I'm going to clear this off. And another utility we can use that is actually a graphical user-based utility is called GTK hash. I already have this installed, but if you want to install that locally, you can say sudo apt install GTK hash, hit enter. You can of course see I have nothing new installed. I already have that in place. And to launch that, we can simply say GTK hash. That's going to launch our graphical user interface. Now let me go ahead and I'm going to save this particular text document. I'm going to save that. I'll just save that into my downloads folder. I'm going to name this test. I'll save that. And let me actually break out of here, and I'm going to go back up into my downloads folder. If I arrow up back through my commands, and inside of that folder, you'll see a test document listed here. So I'm going to launch my GTK hash once again. And now if I go into my file selection area, I'm going to go into my downloads area, and I'm going to choose this test file, and I'm going to click the hash button. And you can see that this generates hash values for my files. Now, similarly, we can use this graphical interface to also check the files in the same way that we looked at in our terminal if we want to compare certain hash values. Let me go back out to the Parrot OS website. I'm going to grab this SHA-1 checksum once again, and I'm going to point that to my Parrot OS file. I'm going to say open. So now we have our Parrot OS ISO file, and in the checkbox, I'm going to paste this SHA-1 checksum. I'm going to tell it to hash. You'll see the progress bar telling us we have about 20 seconds left, and this is going to calculate various hash values. If it happens to match the hash value that I put into the checkbox, then we're going to see a check mark on the right-hand side of this. We should see that next to the SHA-1 box. So we'll let this finish up and we'll see if that is indeed the case. And yes, we do see a check mark here that tells us that this matches the SHA-1 hash value that we put inside. So just a different option than the terminal if you prefer a graphical user interface for doing that. Now let's say we want to actually encrypt a file. Let's close out of this. We, of course, if we say ls and take a look at that, we still have our test file inside. If we say cat test, you can see the contents of that. So I'm going to actually jump back into this file and change that. I'm going to say this is a file that I want to encrypt. I'm going to save it. If I cat test, we can see the contents of this text file. So let's say we want to actually encrypt this. One tool that we can use for that is called Ccrypt. And to install that, you can say sudo apt install Ccrypt. Of course, I do already have this installed, so no changes are made on my side. Let me clear off the terminal just to clean things up a bit. And let's say that we want to encrypt this file. Again, I'll perform that ls command. We see our test file in there. If we cat test, we can see the contents. With Ccrypt installed, if I want to encrypt this, I can say ccrypt-e for encrypt, and I call out the file name. If I say test, it asks me to enter an encryption key. In other words, we're creating a password for this. So I'm going to enter that twice. Now if I perform an ls command, notice we have a .cpt file extension here. So this is now encrypted. Now if I say cat test, you can see that there's no such file or directory. I need to put on the .cpt. So I'll say cat test.cpt. And now look at the contents. They're encrypted. They're unreadable. This is no longer in plain text. Now, if I want to decrypt this, I can say ccrypt-d to decrypt that, followed by the file name test.cpt. Now I need to enter the decryption key. In other words, the password that I set previously. When I do that, it completes. If I perform another ls command, you'll see that the .cpt is now gone. So I can say cat test. Now I can read the contents of this file. So that's an option that you can use for encrypting a file before you send that to someone. And of course, there are many other standalone file encryption tools, but I wanted to show you some of the basics that we have built into Parrot OS. Encrypting files is an extremely secure way that we can share data and be ensured that the data is not being intercepted and interpreted by any unauthorized parties. As we continue our survey of cryptography concepts that you want to be able to describe and know about, let's examine public key infrastructure, or PKI. PKI is an umbrella term for everything used to establish and manage public key encryption, which is one of the most common forms of encryption used on the internet. We've already mentioned public key cryptography in a previous video, which is an asymmetric encryption method, meaning that we use a pair of keys, one public and one private. These keys help us to authenticate the parties which are attempting to communicate with one another. As an example of how this works, let's look at a scenario where we have Bob and Alice, and we have an attacker in between those trying to intercept communications. Bob and Alice want to establish a VPN connection between one another using digital signatures as a verification that they are communicating with the valid parties. They don't want anyone such as this attacker listening in on the conversation and intercepting their data. They are going to use an asymmetrical cryptography method. Remember that this means they're going to use two different keys that work together in order to obscure their data. So what happens is both Bob and Alice will generate a pair of keys, which are different. There's going to be one private key and one public key. We see here that's what Bob has. What Bob does next is use the public key that he has generated to create a digital certification of his identity. This is done by providing his public key to a Trusted Certificate Authority, or CA for short. And a CA simply issues digital certificates for verifying online identities. There are many of those out there that you may have heard of, places like VeriSign, Komodo, and DigiCert. One good way to get your head around what a CA actually is to think of them as a notary. Notaries are authorized to perform certain legal activities on our behalf and in our place, because the notary acts as a stand-in for us to prove our identity. So for example, if we purchase a used car here in the United States with a notarized title, this helps to verify that the seller is the legitimate owner. Both you and the seller recognize that the notary has the authority to verify the identity. So a CA is somewhat similar to that because they are a trusted third-party authority that helps to prove identity. So here, both Bob and Alice trust the certificate authority. What happens next is the CA will provide a digital certificate to Bob. Now, if we open Bob's certificate, we're going to see his public key inside, as well as perhaps some personal information about him. We will also see the certificate authority signature and company information, and some other information related to the CA itself. There would also be a URL that can be visited to verify the validity. Certificates can be revoked either by individuals or by CAs themselves if it's suspected that they have been compromised in any way. They can also expire because they have specific dates during which they are valid. So all of these things can be verified by visiting the URL found inside the digital certificate. Now, Bob has his digital certificate, which contains, among other things, his public key. He would then send a copy of his digital certificate to Alice, which means that Alice now has Bob's public key. Bob then takes a packet and generates a hash value for this packet. Remember when we talked about hashing? Hashing is simply taking an input value and running that through an algorithm to get a unique output value. As long as that input isn't changing, then the output is always going to be the same. He then takes the output hash and he encrypts this using his private key. Once this is done, he takes the encrypted hash and he attaches it to the packet, which he then sends over to Alice. Alice takes the encrypted hash and she decrypts it using Bob's public key. She's going to set aside the hash value output that she gets from this for the time being. She then runs the received packet through the exact same hashing algorithm that Bob did previously. If this hash value output matches the previously decrypted hash that she set aside, then Alice has been able to successfully authenticate Bob. So at this point, Alice knows two things. Number one, she knows that the only person that could have encrypted this data is Bob using Bob's key. And number two, she has assurance that the data integrity is intact. Because if one single bit had changed, if a single 1 or a 0 had flipped, then the hashes would not have matched, and Alice would have known that something is wrong. It's a somewhat complex process that takes a little time to get your mind around, but this is how authentication happens through PKI and digital signatures. Now you may be thinking, this sounds really complex. Why is this important? Well, this exact type of authentication happens in both directions with an IPsec VPN tunnel if the peers are using digital signatures. These signatures are referred to as RSA signatures. These are used by IPsec for authentication in IKE Phase 1 when building a VPN tunnel. So that's a look at public key infrastructure, or PKI. Another important safeguard we want to examine is email encryption. Email is the most widely used communication method for most businesses, so this is a highly targeted asset by attackers. Let's look at considerations from a high level, including the three primary vectors that we want to think about protecting. First is the connection from our clients to the email provider or the email server if we're hosting that on site. Having secure connections here will offer protection from eavesdropping or sniffing attacks, where attackers may be able to obtain login credentials or even the messages themselves and their contents. We also want to protect the messages themselves, and we typically do this by encrypting the messages before they are sent to a recipient. And of course, we want to protect our email archives as well. Our email servers, or even our local email clients, typically archive historical messages, and we don't want these to be available to unauthorized parties. Even if someone gains access to one of our systems, we want to have those protected. We want to ensure that the contents of any archived messages are unreadable by outside parties. Most webmail providers like Gmail or Yahoo, for example, they do have SSL TLS encryption in place in order to protect the connections from the clients to the web services from eavesdropping attacks. Although this is considered to be an end-to-end encryption solution that is offered by these providers, we of course know that these companies themselves are known for their data mining habits. By this I mean that although outside parties may not be able to breach these connections and gather login credentials or email messages, that doesn't mean that the providers themselves don't have access to that information. If you're under a regulatory compliance model, like HIPAA, for example, you might consider a different solution for this to ensure that your email communication is as secure as possible. It's extremely common to see businesses with their own on-site email server, which requires its own solution for protection. There are numerous encryption solutions out there for this, but one I'll mention here is from Barracuda. This solution will encrypt data that is both in transit and data that is at rest or being stored. Barracuda has its own message server center, which requires recipients to access an HTTPS site in order to retrieve any messages, and the message travel is secured by Transport Layer Security, or TLS. Additionally, data at rest is being stored with protected AES 256 encryption. This system allows you to manually choose the individual messages that you want to protect with encryption, or you can even set up policies to automate encrypted messages based on the sender or maybe even the contents inside. So in other words, this solution can automatically recognize sensitive data in the contents of an email message, such as birth dates or social security numbers, and then it would be able to automatically encrypt these selected messages. This particular solution is available both as a cloud-based security service that will integrate with your existing email server, or as a standalone hardware appliance that you can implement into your local network. As I said, this is only one option, and there are many available out there. Zixmail and Mimecast are a couple more that I'll mention. If you're a Google Apps user and your domain is hosted through Google, all of these options mentioned can also integrate with those webmail clients for things like Gmail and Outlook very easily. We've already talked about PKI, Public Key Infrastructure, and this is the primary tool that we use for email encryption. With PKI, we have a public and private key pair. We would, of course, use our private key to encrypt messages before we send those, and we would provide the public key to any recipient in order for them to decrypt the messages. One common mechanism for this in email encryption is PGP, pretty good privacy. If we want to encrypt a message prior to sending that, this is a common way we would do that. And this is the mechanism that we see used in many of the email encryption suites that we've previously mentioned in this video. Just to expand a bit upon how this works, PGP will first compress any email message that we want to encrypt. And the reason for this message compression is it reduces the size of the plain text in the message. And that means that there should be fewer patterns. If we have fewer patterns, that means that the data is harder to crack through analysis. So that's a good thing in this case. PGP will then create a random secret key that is used only once and which is used to encrypt the plain text message. Once the message data is encrypted, we have a ciphertext instead of a plain text message. Our email recipient would, of course, have their own public and private key pair created, and we would have access to that public key. PGP will use this public key to encrypt the random key that was generated. That means that only the intended recipient would be able to decrypt this random key. PGP would then send the encrypted random key to the recipient along with the ciphertext message. The recipient would have to use their own private key to first decrypt the random key, and then they would use the decrypted random key to decrypt the ciphertext and retrieve the email message contents. Again, all of this happens on the back end of these email encryption systems, unbeknownst to the end user in most cases, but I did want you to understand the workflow here. Just to wrap up, a couple of best practices to mention would be to ideally encrypt all of your email communication. We talked about the automation features that are available in some of these encryption suites, where they have the ability to detect sensitive messages and only encrypt those. However, if you think about that, it really just points out messages that would be extremely valuable to an attacker. By encrypting every message, this makes our truly sensitive data that much harder to identify. Whereas if we have specific messages being encrypted, that can allow an attacker to easily pinpoint messages that they can work on. Something that is not necessarily related to encryption but is still a best email practice is to use blacklists and whitelists. These are addresses or domains that would be specifically allowed or disallowed through your email server. There are third-party blacklisting authorities for this, where you can obtain lists of known blacklisted domains, and you can, of course, also maintain those yourself on your own local email server. And, of course, don't forget about email attachment considerations. The email encryption solution you have should be able to accommodate large attachments. If it's not able to do so, then users may be tempted to use more insecure channels for sharing these large attachments. We've looked at some options for ensuring protection through encryption with data in motion, but we also need to consider our data that is at rest, which is being stored on a hard drive. This is achieved through disk encryption. Disk encryption is essentially the process of encoding and scrambling the data that's stored on a physical disk in a way that unauthorized parties cannot view that. This requires a secret key in order to decode the data, just as we've looked at with file encryption in a previous video. We can do this in a couple of ways, either with file level encryption, where we are individually encrypting files themselves, or we can do full disk encryption, where the entire hard drive volume and all of the files inside are encrypted. First, let's talk about some built-in options, starting with Windows. Windows has a protection feature built in called BitLocker. This is a full disk encryption tool, meaning that the entire hard drive gets encrypted. BitLocker is available in Pro and Enterprise editions of Windows, and also for Windows Server, so that is a limitation of BitLocker. If you're a Windows Home user, there's a similar feature called device encryption in the settings, which also encrypts the entire system drive and any secondary drives that may be connected, just as BitLocker does. Although these are functionally almost identical, there are a few differences to note, and that mainly has to do with how the keys are stored. With Windows device encryption on home user devices, this requires a Microsoft account, which will store your configured encryption key in an associated OneDrive account in order to make sure that you do have a recovery key. BitLocker, being used primarily at the enterprise level, has the option to automatically save these keys to your associated Active Directory enterprise account. When we use these options, after you encrypt the hard drive and you log in once again, you'll be prompted for your encryption key. When the device is locked or powered off, all of the files are encrypted, and when we log in, those files will become unlocked and allow the system to operate just as though it were unencrypted. Any new files placed on the system would automatically be encrypted on the fly to ensure that everything is still being protected. Also note that with BitLocker, you can set an additional PIN, or you can require the insertion of a removable device like a flash drive in order to unlock the normal startup process. So that's a further protection mechanism that we have available. If you're a Mac OS user, there's a similar option called File Vault. This offers full disk encryption as well, just like BitLocker, and it requires an encryption key to be entered during the startup in order to decode the hard drive data. Recent versions of Mac OS have the ability to use an iCloud account to unlock the encrypted disk and also to recover the encryption key if that is lost. If we're talking about Linux-based systems, there are many tools available for that, including the popular and open source VeraCrypt. VeraCrypt is a successor to the original TrueCrypt software, and VeraCrypt is still being actively developed and updated with the latest encryption standards. Functionally, this is the same as File Vault and BitLocker, offering the complete encryption of a device or a hard drive partition. But we additionally have the ability to create a virtual volume, known as an encrypted container. This can be created anywhere on the device, and it would behave as a typical folder directory on the system. But this will be specifically an encrypted volume, leaving the rest of the hard drive structure untouched and unencrypted. This would allow us to place specific files inside of that folder for encryption, and we can access those files through the encryption key when we need them. VeraCrypt, of course, not only works with Linux-based systems, but it's also available for both Windows and Mac OS as well. Regardless of which solution you're using, there are a few considerations we should mention here. First is that the initial encryption of the device, depending on the disk size, and especially if this is full disk encryption, that could take up to several hours to perform. Although you can still use your device normally during this time, just know that you need to be able to have the device powered on for several hours in order for this to complete in most cases. It's also important that you keep track of your encryption key in a secure place. If you lose your key, and you don't have that saved anywhere, such as OneDrive or iCloud backup options that we mentioned earlier, then your data is going to be gone forever. These encryption standards that are used are extremely robust and not capable of being bypassed in most cases. And finally, consider the age of your device and how full disk encryption may affect performance. This is especially true if you're using a traditional hard disk storage device. Generally speaking, SSDs, which are based on flash memory, they offer much faster performance, and these performance issues may be exaggerated with full disk encryption. With SSDs, full disk encryption is not as likely to impact your performance in a noticeable way as opposed to HDDs. Cryptographic attacks against our encrypted information is often referred to as cryptanalysis. So you might see these attacks referred to as either cryptanalysis attacks or cryptographic attacks. Cryptanalysis itself is defined as any method of decrypting ciphertext into plain text. So this is essentially the opposite of cryptography. This can involve various methods in order to try and understand and interpret the data, and the assumption is that someone has been able to obtain our encrypted information in some way in order to have the ability to analyze the cryptography. It should be noted that as our encryption standards have evolved into stronger algorithms, as long as we use these modern and stronger protections, this has become increasingly difficult. The main danger for us here is using legacy or insecure cryptography. We can group these attacks into several broad categories, starting with what we refer to as a ciphertext-only attack, or COA. This is named as such because the only thing an attacker needs access and has access to is the encrypted data itself. Attackers would be working under some assumptions, and that assumption would be that although they don't know the plain text equivalent of the data, they may assume a set of characters, or they may assume the language used. For example, they may assume that in the plain text this would be in English. The original Wi-Fi security protocol WEP is an example of this. That was susceptible to many ciphertext-only attacks. One of the ways this works is with known standard protocol data messages. So for example, with WEP, there are certain protocol messages known to be sent and received. If an attacker knows certain plain text contents like this, then they can begin to try and decode the data and draw correlations between the ciphertext and the plain text. One of the most successful methods for this is something called frequency analysis, where an attacker will analyze the ciphertext looking for popular letters inside that appear over and over and over. For example, if the letter Z is very commonly seen in the cipher, maybe that's the most commonly seen letter, then they might assume that this perhaps correlates to one of the most popular English letters, maybe the letter E. Although ciphertext-only attacks are the most difficult due to the amount of trial and error and the analysis involved, this is typically one of the most successful tactics because, as we've said, no other information is needed other than the ciphertext itself. The next category is known plain text attacks, or KPA. With these attacks, the attacker has access not only to the ciphertext, but also to the corresponding plain text values. Our modern ciphers are generally considered to be very resistant to these because we can add secret keys to the encryption to give that more strength. An example of this was the old PK-zip encryption method, which used legacy algorithms to create encrypted zip files. By having an encrypted file along with the original unencrypted version, it was possible to discover the secret key used. As you can imagine, this is a relatively easy attack to perform, but again, it's not very common with our modern encryption standards. Somewhat related to KPAs are CPAs, chosen plain text attacks. This is a relatively low success rate attack, again due to those modern advancements in encryption. With this type of attack, an attacker will encrypt large amounts of arbitrary plain text data with the same encryption as the ciphertext data in order to observe the corresponding ciphertext that gets generated. By doing this, they're trying to discover the encryption key used for the ciphertext that they're attacking. Similarly, we also have adaptive chosen plaintext attacks, or ACPAs. This is a subset type of chosen plaintext attack. This is more powerful than a basic chosen plaintext attack, but generally less common because it requires interaction with the encryption device itself. Here, the attacker will use a smaller amount of chosen plaintext. They would encrypt that numerous times over and over in order to receive ciphertext outputs that they would analyze for patterns. And we have something more basic, which are dictionary attacks. This would consist of an attacker constructing a so-called dictionary of plain text with their associated ciphertexts. These lists would be curated over long periods of time, maybe from their own experiences or supplemented by online resources. Anytime an attacker obtains any ciphertext, they would reference their dictionary to try and find any corresponding plaintext. As we've seen in this course already, dictionary attacks are commonly used against passwords and also can be used to decrypt keys and decode ciphertext. There are tools within Parrot OS that we've looked at previously, such as Hashcat, which will assist in any cryptanalysis that you want to perform, but there are also many online resources to automate things by searching through well-known hashes or even trying to actively decrypt the hashes. If we go into my Parrot OS here, just to give you an example of how this might work, let's use an algorithm with a well-known weakness such as MD5, and let's generate a hash for that. I'm going to say here in my terminal, echo-n, and I'm going to use the value hello world. I'm going to close those quotation marks. I'm going to say pipe, and I'm going to say MD5 sum. This is going to generate an MD5 hash value for the text hello world. So I'm going to copy this. There are various websites dedicated to MD5 decryption, but just as an example here, let's go to this one that we see on the screen, and let's paste in our hash value. Let's click decrypt, and as simple as that, you can see that this spit out the actual plaintext value for this hash, which is hello world. Very quickly, this reversed it for us. So cryptanalysis is an extremely involved and deep concentration topic, but if you're interested in learning more about that, I would point you to a place called the CryptTool portal at cryptool.org. This is a free tool to learn more about various ciphers and coding methods. You can use this directly in the browser, or there are various options down here depending on your operating system. You can see versions for Windows, Mac OS, and Linux. It's a great resource if you're interested in learning more specifically about cryptography and cryptanalysis. To wrap things up, let's talk about some important countermeasures for protection against cryptographic attacks. It's worth noting once again that modern cryptographic standards make these types of attacks much more difficult than they used to be. Most of these attack concepts that we've looked at are theoretical, coming from research and academia proof of concepts. Although they may be impractical in many cases, they are still possible, and we still need to ensure that we are adhering to our best practices if we want to avoid these situations. If we're improperly implementing modern security, or if we're using legacy standards, then obviously we open ourselves up to well-known problems. So let's talk about some best practices. First, let's consider places where symmetric keys are implemented. Symmetric meaning that we have a single secret key used to both encrypt and decrypt the data. A common example is AES encryption, one of the most well-known and widely used symmetric encryption algorithms today. The best practice recommendation for using symmetric keys are that they should be at least 168 bits and preferably 256 bits in order to have the most attack resistance. Asymmetric key algorithms, of course, use a public and private key pair mathematically linked together in order to encrypt and decrypt data. We commonly see this used with RSA encryption and with TLS SSL during the TLS handshake. We see a much larger best practice recommendation here for asymmetric keys, where they should be at least 1,536 bits, and ideally a minimum of 2,048 bits. In fact, modern SSL RSA key length is typically 2,048 bits in size. Now, the reason we see a much larger key size with asymmetric algorithms as opposed to symmetric algorithms is that there are certain patterns within the key pairs that might be easily reversed, if not for the large amount of bits. With any file hashing, we need to consider this as well. If you have a database of usernames and passwords, this can be used for password verification. We most definitely want to hash any stored credentials and sensitive databases. And the way this might work is the server would store a hashed equivalent of the password rather than the actual plain text version. When a user enters their password into maybe a web application, that password hash value would be sent to the server and compared to the hash value in the database. So this is a safety mechanism for ensuring that passwords are not passed or stored in plain text. The recommendation for hashing would be to use something from the SHA-2 family or higher, ideally SHA-256 or higher, for best protection against attacks. Another technique for even stronger security is salting a hash value. If you think about a password, we may append or prepend additional values onto that password. If we have the original unsalted password that we see here, and we have a salt value of secure, we would add those two values together before hashing them, which is going to output a much larger hash output value, and it's going to make it much more difficult to reverse. If we're using salting, we also want to consider using a one-time only salt value. We don't want to give the same salt value to every password that we're salting. And generally speaking, anywhere in our systems or network that we may be using legacy standards, we want to update those. This would include, of course, wireless encryption that's in use, drive encryption standards, and implementing traffic encryption through mechanisms like VPNs where that may be relevant.